All right, this is an example of balancing a chemical equation. Here we have a chemical, hydrogen peroxide, you're familiar with. Here we have a chemical, water. Oxygen is also present, right there. And the formula for hydrogen peroxide is H2O2. We can't change that because that's the chemical formula. You can't change the subscripts. This is oxygen in air. Of course, it's a gas at room temperature, bouncing around really fast. Okay, it contains 2 oxygen. That's why there's a subscript of 2 in 1 molecule. Here's water molecule, one of the most famous chemical formulas in the world, except for the way organic chemists write it. They write it HOH. That's the same thing as H2O. 2 hydrogen, 1 oxygen. Okay, the problem is this is not balanced. We are breaking the law. We have to obey the law, the conservation of mass, and make sure that everything that goes in also comes out. This is the middle, the yield sign. Everything on the 2 sides needs to balance. Just like on a balance, okay? Just like on a balance, the 2 sides need to add up to the same mass. The only way they can be the same mass is if we have the same number of the same atoms of every element on each side. So let's see, 2 hydrogen, check, that's good, that's balanced. 2 oxygen, 1, 2, 3 oxygen. And you can see that here, okay, because all of the coefficients are 1, they're invisible ones. You could imagine 1s in all these places. 1 times 2 is 2. 1 times 1 is 1. The total on this side is 3. This side is 2. 3 to 2. That's one of the techniques in balancing. If you ever run into a situation where there's odd on one side, even on another, make the odd side even to fix that. So the number one way that we fix that is find which part over here is making it odd. Well, this is 2, that's an even number. But this is the odd one out. So in order to make this work, we know we're going to have to make the odd side even. We're going to have to double, put a coefficient of 2 in front of the odd part. That gives us 2 water molecules. That's what that 2 means. It multiplies by the whole thing. It means we have 2 water molecules. But now notice that has messed up the balance of hydrogen because now we have 4 hydrogen on this side. 1, 2, 3, 4. 2 times 2, 4 hydrogen. But we only have 2 on this side. Well, the only way to get more hydrogen on this side is to have more hydrogen peroxide. So then I could put a coefficient of 2 here. That coefficient means that I get another hydrogen peroxide on this side. They're not merged into one. They're 2 separate molecules, but it means I need 2 of them for this to work. Okay, so let me slide these downward to be sort of in the middle here. And then let's put the oxygen right there. So now let's see. You can visually see that 1, 2 oxygen here, 2 oxygen there. 2 oxygen here, 2 oxygen there. There's 4 total on this side, 4 total on that side. There's 4 total hydrogen atoms on this side, 4 total hydrogen on that side. By the way, this reaction, even though it is going here, it is going in here, all just like this, inside. Okay, and now by the way, this is balanced. So I like to put a little check if I think it's balanced. Okay, it's going on in here, but we can speed it up with the catalyst. The catalyst I use in my demo is called manganese dioxide. This little powder that I put in speeds the reaction up a lot. So one way to show a catalyst is to put it above the yield sign, like right there, or to write above the yield sign what the catalyst is, like MnO, okay? MnO2, excuse me, manganese dioxide, not magnesium, manganese. Or another thing I could do is I could put it on both sides. Let's see, I could put it over here. I don't know, I don't have room for it, but let's say I have a plus MnO2 over here, and I could put it on this side, plus MnO2 on this side. But of course, that's not going to affect balancing. I don't have room to put it. It would actually be written separately. But if you see the same exact chemical on both sides, you can always ignore it when it comes to balancing. Also when it comes to reaction type. So what kind of reaction is this? Do you think this is combustion because it has oxygen? it is actually very, very far from combustion because actually oxygen is on the wrong side. For combustion, you need oxygen on the other side, on the reactant side. This side is called the product side. So when you have oxygen on the product side, it is definitely not combustion. Okay? So what kind of reaction is this? One reactant. Even though there's two molecules of it, it's one reactant making two products. What kind of reaction does that sound like? Which of the 5 reaction types? We said it's not combustion. It is, which of the other 4? It is decomposition, because it's one chemical breaking into 2 others. Okay, so that is an example of a fairly easy reaction to balance. Okay, so we're going to balance this equation. It's a reaction between phosphorus trichloride, which I'm representing right here, PCl3, and water, producing phosphorus acid, phosphorus OUS acid, H3PO3, and hydrochloric acid. So it's interesting, this reaction makes 2 acids. It's clearly out of balance. What do we not want to start with? We don't want to start with hydrogen. See how it's split up? It's actually the only one that is split up on one side. Do the hydrogen last, obviously. Okay, so what should I do first? I think I'm going to start with the chlorine. Notice that there's 3 chlorine here. 1, 2, 3, and there's only 1 over there. Well, I can fix that. All I have to do, put a coefficient of 3 right there. If I put a 3 there, that means 3 of them. Now, this is not the ideal way to show hydrochloric acid. This is a bootleg way to show it, because actually it's not an ionic compound. This makes it look like it's an ionic compound. It's a polar molecule, so really, let's imagine that you can't see those pluses and minuses there. But it means 3 of the HCl's. These are all separate molecules, actually, like this. Okay, so now the chlorine, or the chloride, is balanced. And now we want to deal with, what else can we deal with? Well, phosphorus. Okay, notice there's 1 on each side. Don't worry about this charge shown here. That's for the polyatomic ion. Let's, again, ignore those when it's in its molecular form. Just ignore these charges. I just didn't have the right ones for this modeling. So there's 1 phosphorus on each side. That's fine. Can't do anything about that. Oh yeah, oxygen. Since we want to deal with hydrogen last, let's do oxygen. Well, there's 3 oxygen here, 1, 2, 3, only 1 here. Well, if I multiply the water by a coefficient of 3, that means boom, boom, 3 separate water molecules. Now I've got 3 oxygen atoms here, 3 times 1, and 3 oxygen atoms here, 1 times 3. Okay, good. Last thing is deal with the hydrogen. So how many hydrogen do we have total on this side? There's 3 there, and there's 3 there, total of 6. How many hydrogen do we have over here? 6. 2, 4, 6. Boom! Sometimes one of the elements will come out in the wash. When you're balancing one, the other will just fall into place like dominoes. So that's a pretty easy one to balance. Notice it just needed a couple of coefficients of 3. And what are the coefficients here? The coefficients are invisible ones. So notice if they were all 3, we would divide through by 3, but you can't because there is that coefficient, those coefficients of 1. Okay, we are going to balance this equation right now. This is an interesting equation because it involves this chemical, NH3, which is known as ammonia. Ammonia is a very common chemical. It has a tetrahedral form, but you can't see the one on top because that's a pair of electrons that's not bonded. Okay, ammonia was named after a temple in Libya. That's an interesting story. I'll tell you about that if you want to know. It was named after a god, Jupiter Ammon. That's where ammonia comes from. Not to be confused with ammonium. Ammonium is NH4 positive. This is a polyatomic ion, whereas that is a molecule. Ammonia, ammonium. The only difference is the ending. And if you have household ammonia, which is a cleaner, well, in solution, ammonia always generates some ammonium. So you actually do have some in there. All right. We're taking that and we're reacting it with oxygen. Remember, O2 is just called oxygen. And if you have a reaction with oxygen, well, that's a dead giveaway. Which type of reaction is it? Which reaction type? There's one category of reaction that is a reaction with oxygen always. Very easy to identify. And that is combustion. Combustion, you're reacting a chemical with oxygen, making a compound with oxygen. But a better way to look at it for this reaction is this way, okay? Because what we're really reacting is a compound reacting with oxygen, producing two chemicals that both contain oxygen. This is another way of showing the combustion generic pattern. So any reaction with oxygen is always, always combustion. Okay, so that's good. And then what are we producing? The products, which is this side, this produces these. The yield sign shows you where the products start. Most famous chemical formula in the world, H2O, H2O. Okay, organic chemists write it HOH. This is, of course, water. Okay, water is a very, very common product. Maybe that's why we have water everywhere covering the earth. It's a very common product. The other product here isn't quite so common, not quite as good. This is NO, nitric oxide. This is an oxide of nitrogen. Oxides of nitrogen form when there's a reaction, well, this can make them, or if you get a reaction between nitrogen and oxygen, which isn't too likely in the atmosphere, but it can happen under certain conditions. Oxygen is a clear gas, we breathe it. Nitrogen is a clear gas, we breathe it. We breathe these, that's fine. But we don't want to breathe these, okay? NO, N2O, and NO2, oxides of nitrogen. Okay, this one makes you laugh, this one makes you cry, this one makes you die. So we would not really do this reaction in our lab. In fact, when this reaction happens in like an industrial site, a lot of times they have to clear out the town, evacuate the town because of these products. They can be really, really toxic, really, really hazardous. Now, the great thing about this reaction though isn't that we're going to do it in our lab and do the experiment, it's that it's really good to balance because we must obey this law. And this is breaking the law of chemistry, the conservation of mass. Right here, it's just breaking the law. Why? Because nitrogen's fine, okay, even oxygen is fine, but hydrogen is not. Remember, you can figure out either looking at these models how many are present, or looking at the chemical formula. Remember that everything that's not written is an invisible one. So imagine that's a 1, that's a 1. Anytime you don't see a number, imagine that it's actually an invisible 1 that's there, okay? So we've got 1 nitrogen, okay? 1 nitrogen. We've got 2 oxygen here, and we've got 1 oxygen, 1 oxygen. That's 2 on this side. 2 and 2, that's fine. Hydrogen is the problem. For hydrogen, notice there's 3 on this side, 1, 2, 3, and there's only 2 on this side, 1, 2. So if you have 3 on one side and 2 on another, what does that remind you of? What's the problem here? What's the way to fix this? That's one of the techniques for balancing equations. It's odd, even. So when you have an odd-even situation, it doesn't matter which one is more, you got to make the odd side even. So to make the odd side even, we usually just double it, put a 2 right there, and now that means 2 ammonia molecules. That's what that 2 means. 2 times this. Okay, wait a second, I just threw off the nitrogen. Better fix that right away. I'll put a 2 here now, coefficient of 2 in front of the nitric oxide, and now we fix the nitrogen. And the reason we did this was to balance the hydrogen, and now we can. Because there was no way to make this an odd number, so we had to make this even. But now we have 6, which is an even number. So if you've got 6 hydrogen here, 2 times 3, 1, 2, 3, 4, 5, 6, I can get 6 here. What do I need to multiply the water by? How many of these do I need? How many of these? What's the coefficient? I need a 3. I need a 3 right there. And that, of course, means 2, 3 water molecules. I'll try to show them separately. They're not all merged together, but I might have to put them a little tight here for space. But they're separate water molecules. It's just that we have 3 of them. That's why it multiplies by the whole chemical. The coefficient multiplies by the whole chemical. Okay, so now we've got 6 hydrogen, 2 nitrogen, 2 nitrogen. Now it's time to fix the oxygen. The reason we do the oxygen last is because it is split up on this side. That oxygen is in 2 chemicals. So we always want to deal with those last. So let's see, we have 3 oxygen here and 2 oxygen here. 3 plus 2 is 5 oxygen, and you can see them here, 5 oxygen atoms. Over here we've got 2. 5 and 2. What does that sound like to you? Odd, even. Again, this happens twice in this particular equation. This is why this is such a good example. 5 and 2, well, what do I have to do to fix this? I can never get this to be 5. Whatever I multiply it by, any whole number will never get us to 5. So I got to make this side even first. So you got to make the odd side even though it's got way more oxygen. Doesn't matter. So this isn't making it odd. This is 2. That's fine. It's this. This 3 is making it odd. So I've got to double that. That's the part you double. The part that is making it an odd number, and now it's not an odd number anymore. So now, first of all, what that does is that throws off the hydrogen. So let's just fix that problem right away. How many hydrogen does that make? 6 times 2? Okay. Oh, by the way, so now that I put a 6 there, I better put the water molecules on. Okay, 6 water molecules there. They're all separate ones. I just have to squeeze them close together, so for space, I think that's about the best way I can do it. Okay, 6 water molecules here. That gives me 12 hydrogen. Well, how am I going to get 12 hydrogen over here? Well, what do I have to multiply the 3 by to get 12? I have to multiply it by a 4. So I'm changing this to a 4 now, kind of doubling it. A lot of times when you double one thing, you have to double other things too. So again, notice I have to cram these in here. So now we've got 4 ammonia molecules, which gives me 12 hydrogen. 3, 6, 9, 12 hydrogen. Hydrogen is balanced. Oh wait, look what we just did. We just threw off the nitrogen. So now nitrogen is 4. How can I make this 4 nitrogen? Change this to a 4. Notice why you want to be able to erase your numbers, right? You want to balance with a pencil or with a dry erase marker. 3, 4. Okay, so that's 4 nitric oxides. Maybe I'll set them off like that a little bit so you can see that they're different. And that, of course, gives me 4 nitrogen. 1, 2, 3, 4. 4 times 1. 4 nitrogen. So nitrogen is balanced. Hydrogen is balanced. Oh, we never quite finished the oxygen. We did do the odd-even technique, but we never finished it up. But now let's do that. We've got 2 oxygen on this side, obviously. 2 times 1. 2 oxygen. Okay? We got way more on this side. Okay, 6 times 1 is 6. 4 times 1 is 4. 6 plus 4, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygen atoms. So you got 10 on this side, and we got 2 on this side. Is that odd even? It is not odd even because 10 is an even number as well, so it's no problem. Barely an inconvenience. All we have to do is turn this into 10 oxygen. What coefficient do I need here? What coefficient do I need to make this 10? I need the number 5. 5. And that means, of course, 1, 2, 3, 4, 5 oxygen molecules. Okay, so everything on this side is balanced by everything on this side. This is where the atoms started. This is where they ended up. Before the reaction, after the reaction. Reactants, products. And just to make sure, we've got 2, 4, 6, 8, 10 oxygen, and we already counted 10 over there. Everything's now balanced. I can put a little check. The only time this might be wrong, if you have everything the same on both sides, is if you can divide all the coefficients by 2 or 3. But notice, you can't divide through by 2 because that's an odd number. You can't divide by 3 for sure because only this number is divisible by 3. That's the only time you might be wrong if you think it's balanced on both sides, is if you've doubled the whole thing. Because this would work if you doubled it. So now, we've obeyed the law, conservation of mass. We've got a balanced chemical equation. Okay, this is the combustion of ammonia producing water and nitric oxide. And isn't it funny that the only little tiny difference at the beginning was only one little hydrogen difference? That was the only thing that was off. The smallest atom in the universe, one atom of hydrogen, and yet that led to all this. That's why this is such a great one, because we had to use our techniques, and it involves quite a few changes. So most equations are much easier to balance than this. Many equations don't involve any coefficients, just ones that you don't even change. Some of them might have like a 2 here or a 3 there. This is an unusually hard one. So don't expect most equations to require this much work. So we just obeyed the law of conservation of mass. We did it. Okay, so this time we're going to try to balance an equation that is hard for even chemistry teachers to balance. One of the hardest equations to balance that there is. And that's because it's a multiple step reaction. So these are the initial reactants and these are the final products. If you look at this reaction, we used to use this to start the thermite back in the day. See the little singe marks? I put it a little too close to the demo, I guess. This reactant involves some polyatomic ions. Can you observe any polyatomic ions in this equation? I think one of them is really obvious. Why is it so obvious? Why is it obvious? Because it's in parentheses. If you ever see a chemical that's in parentheses, that is a polyatomic ion. Well, which one is it? That is hydroxide, OH-. That is the functional group for alcohols. It's also in many, many bases. A lot of bases are hydroxides of an alkali metal. Can you see another polyatomic ion? Well, there's one, MnO4. It's not given away, there's only one of them. That is called permanganate. This is called potassium permanganate. Are there any other polyatomic ions present? Oh, I see one more. This one, CO3, carbonate, CO3 2- carbonate. So there's 3 polyatomic ions present. Well, that should make this easy, right? Because usually if there's polyatomic ions present, well, then you can sort of balance them on the 2 sides, and it really helps you, it saves a lot of time. But where did they go? Where's the permanganate over here? Where's the hydroxide over here? Where is the carbonate on this side? So the polyatomic ions are not present on both sides. You could sort of say these ones are destroyed by the reaction. And if that's the case, well, then you can't use them to help you balance. Well, so much for that. Actually, one of them is not actually destroyed, if you really think about it. But, you know, I'm just going to ignore that for now. Okay. So I balanced this years ago, but not for a while. So I'm trying to put out of my mind anything I know about it. I'm just going to try to use the techniques that I've shown you to try to balance this equation. And what's the first technique? Start with something that is once on each side. So let's see, potassium. Well, there's a potassium right there. Potassium is right here, and it's right there. That's once on each side, that's okay. What about Mn? What is Mn? Manganese. Manganese is once right there, and it's also once right there. It's not anywhere else on this side. So those are good ones to start with. Are they in different amounts? Yes. Okay, well, what else is present once on each side? Let's see, maybe carbon is. Carbon right there. And, oh, there's a carbon, okay. And is there any more carbon? Yes. Oh, so carbon is actually split up. So that's not a good one to start with. We'll deal with the carbon after we deal with those other ones. Is anything else present once on each side? Well, what about the hydrogen? Okay, so hydrogen is there and there. But that's all in one chemical, so that's okay. And where is it over here? It's only there. So actually hydrogen is not a bad one to start with. Okay, we could actually do hydrogen also. So that's a good one to start with. What about the oxygen? Okay, here's oxygen. There's oxygen. Oh, there's oxygen. And oh, there's oxygen. There's oxygen. There's oxygen. And there's oxygen. Well, forget about oxygen. Oxygen is the last thing we want to start with. It is in every single one of these compounds. That means it would be incredibly hard to balance the oxygen at the beginning. We want to do the oxygen last. And then just before that, we probably want to do the carbon. And the ones we want to do first, potassium, manganese, or maybe even hydrogen. Because hydrogen is once on each side in different amounts, why don't we start with the hydrogen this time? Actually, why not? Let's just do it. So hydrogen is present on this side. How many hydrogen are located here? That's a polyatomic ion, meaning it's multiplied by 3, and then there's 5 more. So with a coefficient of 1, that means 8 hydrogen on this side. And then how many hydrogen are located here? Obviously 2. So how can I make this 8? Okay, well, I need to multiply that. I need to multiply this by a coefficient of 4, and then I've got 8 hydrogen on this side. So hydrogen, 8 and 8, boom, done. Now let's deal with the potassium. Potassium, there's 1 on this side, and there's 2 on this side. Okay, so how can I make this one 2? Well, just double it. Just double it right there. Boom. 2 potassium on each side. And then, oh, that also gives me 2 manganese, right? And I've got 2 manganese on this side, so that's good. 2 and 2. So look, we've already got 3 of the 5 balanced. So this should be really, really easy, right? How many carbon do I have here? Okay, we did the 3 that are easy. So now the carbon would be the next one, and the last one would be the oxygen. So we've got 3 carbon. And how many carbon over here? Well, here's 1 carbon. Oh, here's another carbon. 2. 3 and 2. 3 carbons on this side, 2 carbons on this side. What does that remind you of? 3 and 2, odd, even. So what do we do when we have odd, even? We make the odd side even. Even if it's more, we make the odd side even. So I'm going to double this now, getting a lot of 2s and 4s here. And now I've got 6 carbon. That changes this to a 6. And now I can make this match. How can I make this into 6 carbon? Well, the easy way would be to not mess with the potassium or the manganese, not mess with either one of those, but only mess with this one. If this is only 1 carbon, okay, well then I could make this the rest of them. I could make this 5 of them. Boom. 5 plus 1 is 6, so then they're balanced. So that's pretty good. So we've got 6 carbon, 5 carbon and 1 carbon, 6 carbon. We've got potassium, manganese, carbon, hydrogen, boom, 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 boom. One more thing, oxygen. So let's see. If the oxygen just falls into place, brrr, then that's great. That is just great. So let's see, how many oxygen do we have right here? Okay, well let's see, I've got to add these up now. That gives me 8 oxygen right there. And then how many are here? Well, that's 3 times 2, 6, that's 14 total. 15 total oxygen atoms on this side. Okay, so oxygen is all over the place here. So let me just be careful. 3 there, 3 there, 10 there, and 4. Okay, so, well that's 14. Oh, plus 6, that's 20. So yeah, everything balances but the oxygen, which is a big problem. You can't have even the slightest thing out of balance. So how are we going to fix that? Well, let's see. Got 20 oxygen on this side, 14 on this side. Something is not working here. Something is not working. Sometimes, if you're in a situation like this, it might help to sort of double all the coefficients and then adjust from there. So let's see if we can sort of do that. Let's see if we sort of double everything and just see where that leaves us. And then we might be able to adjust from there. So that would be a 4. That would be a 4. What would this one be? 2. This would be a 2. This would be a 10. This is crazy. This is crazy. And 8. Okay. So then, let's just see what our numbers are if I do this. Most of them should just be doubled. Like that should be 4 potassium, 4 potassium, 4 manganese, 4 manganese. Let's deal with the hydrogen. So that's 8 hydrogen in here times 4, 32 hydrogen, right? 8, 32 hydrogen. Okay, and then how would I get 32 hydrogen over here? What coefficient would I need? I would need a coefficient of 16. That would give me 32 hydrogen on both sides. Okay, and then how many carbon would this be? 4 times 3, 4 times 3, that is 12 carbon. And how many carbon do I have over here? I've got 10 carbon, right? And 2 carbon. Oh, good. Carbon is good. That's pretty cool, pretty cool. All right, so let's see. What else do we have to add up? Well, the oxygen, of course. Everything matches, except for the oxygen. So let's see. Oxygen, we've got 16 right there. And we've got, that's a 3, right? So then 12. Okay, 16, 28 oxygen. Let's see what we've got over here for oxygen. We've got 6. We've got 10. Okay. 22. And then we've got 16 more. So that's 26 plus 12. That's 38. Oops. So the oxygen is a little bit off. All right, so let's see here. What's a good thing to do? Well, we don't want to mess with the potassium and the manganese because those seem to be balanced. We want to really mess with the, what do we want to mess with? I guess the carbon would be the next one. So we don't want to mess with this coefficient because if we did, it would throw off the hydrogen. So we've got 12 carbons. Let's see if there's another way to split the carbons. The only problem is if you do anything over here, it would mess with the potassium and the manganese. So let's see, if we have 12 carbons on this side and then 12 carbons on that side, well, it's either 10 and 2, or we could split it any other combination that adds up to 12, like 6 and 6. You could split it 6 and 6, but this would cause a lot of chaos. Well, let's try it. Let's try splitting it in half. Let's try splitting the carbon in half. The reason I'm doing this is because after the potassium and the manganese, the carbon is the least split one on here. Oxygen's the last one. Now this is going to throw everything into craziness. So let's just deal with it. Maybe this will work. You got to try to deal with the carbon because I can tell that the carbon is split twice. That's the one we're going to have to deal with. Okay. So, and that would not change the hydrogen. That would be 32. And that would be 32 over there still. And it would not change the carbon. That would be 12 there. So now, and we still have 12 over here. That's what we're trying to start with. So now we're going from the hydrogen directly to the carbon and dealing with the pieces as they fall. So this gives me 12 potassium on this side. So how could I make this? How could I make this into 12 potassium? But I have to put a 12. I'd have to put a 12 right here, wouldn't I? Put a 12 right here. And then that's 12 manganese. Okay. So then, if we want to have 12 manganese, well then this better be a 6 right there. So we'd have 12 potassium, 12 manganese, and 12 manganese. Lots of 12s here. And then maybe the oxygen is going to cooperate. Please cooperate. So how many oxygen do we have over here? It's 48. Can we write it down? And then how many oxygen are here? That's 3 times 4. That's 12. That's 60. Interesting. These look like kind of good numbers. I don't know. They look good. 60 oxygen over here. Maybe this side will be 60? Let's see. 18 oxygen right there. 18 oxygen right there. Okay, we got 12 oxygen right there. And we've got 16 oxygen right there. So let's see. 18 plus 18 equals plus 12 equals plus 16 equals 64. So no, it does not balance the oxygen. Although it's pretty close, but that's not good enough. That's breaking the law. We must obey the law. Oh man, this is a hard one, right? So again, I'm going to try the same strategy again, keeping the carbon and hydrogen matched up, right? Because, I don't know, and then just trying to split the difference another way. So instead of splitting it 6 and 6, I could try splitting it 7 and 5 or 5 and 7. Let's try the 7 and 5. 7 and 5. And if that doesn't work, I'll try the 5 and 7. Oh man, and of course that's going to change everything. That gives me 14 potassium. Well then, of course, if you have 14 potassium there, then this coefficient has to be the full 14, and then that's 14 manganese, right? So then what does this have to be to get 7? So then we get 14 potassium, 14 manganese, and we got 14 manganese. Okay, this is looking good. So now we get everything again, except for the oxygen, and maybe the oxygen is going to just fall into place. Maybe this time, oxygen is going to fall into place. Okay, so let me just do this very carefully because I feel like I'm losing my mind. 14 times 4, 56, plus, how many oxygen are here? This is 3 times 4, that's 12. So 12 equals, what? No, I did a typo. Times 4 equals, plus 12 equals, okay, 68. Well, you know what? Whatever, 68 oxygen on that side. That's a lot of oxygen. How many oxygen are on this side? Okay, so 7 times 3, 21. 7 times 3, 21. 5 times 2 is 10. And 16 more. Okay, well, let's see. 21 plus 21 plus 10 plus 16 gives, oh my gosh! Woo! 68! So, woohoo! Oh yes! Wait, let me double check this. Is this right? Okay, so just to be clear, this wasn't easy to balance. 14 potassium. 14 potassium. Boom. 14 manganese. 14 manganese. Boom. Okay, well, let's see. We just did the oxygen. Let's do the carbon. 12 carbon and 5 and 7 is 12 carbon. And hydrogen. Okay, this is 8 times 4, 32. And 16 times 2 is 32. Oh my gosh, oh my gosh. Wow, balanced it. And you know what, if that hadn't worked, I was thinking about, like, if that didn't work, I was thinking about splitting it the other way, like a 5 there and a 7 there. So it could have gone either way if I had started the other way. And I was thinking about then, like a 4 and 8. Because eventually, the carbon was the key to solving this, because the carbon is only split up one time. And so after you deal with the easy ones, well then carbon has to be dealt with next. Deal with the oxygen last. Amazingly, that worked out. It probably could have taken me a few more tries. Okay, amazingly. So this is the balanced chemical equation, and I think I have it here somewhere. I didn't look at it beforehand. Obviously, you can sort of tell. And does this match? Yeah. Yes. Okay. I did not look at this, believe me. If I had looked at that, it would have gone a lot faster. And I think what I sometimes do is I give students a hint, because that's such a hard one to balance. I sometimes give them this one, I think. I give them one of the coefficients. But I did not look at this beforehand. I haven't balanced this one for a while, for years. So that worked out. It's just not easy. That's a ridiculous equation. That's about as hard as an equation can possibly be to balance. What I forgot to mention at the beginning is that potassium permanganate is a beautiful black, shiny crystal substance, kind of sparkly, and it's very easy to get reacting. It's very reactive. And if you react it with glycerin, which is like a goopy liquid, an organic liquid, it'll give off a lot of energy. And that's why we use this to start the thermite reaction. But then when our potassium permanganate started getting lower quality from the chemical supply companies, we had to stop doing it this way because it wasn't reliable. It became a gray powder. It wasn't so sparkly, very suspicious. Didn't react as well. Okay? By the way, glycerin on its own is just a goopy organic sort of syrupy substance, but you don't want to mix it with nitric acid. No, no, no. That makes nitroglycerin. Nitroglycerin was banned in the USA for about a century because it's an explosive liquid. You don't want to have nitroglycerin lying around. Just ask Alfred Nobel. We'll talk about that, or his brother. We'll talk about that a little bit later. But amazingly, this worked out. And I did not cheat. Don't worry. If I had cheated, I would have made myself look way smarter than that. So this is a ridiculously hard equation to balance. What reaction type is it? Well, it's a lot of reaction types. It's decomposition, it's combustion. So this is many steps. That's why this is so hard. Each one of them would not have been so hard to balance. But putting it from the initial reactants to the final products is what makes it ridiculous to balance.